So we're going to begin talking about sequences here. Sequences are fundamental to the study of infinite series. A sequence is a list of numbers. We might have a list of terms like a sub 1, a sub 2, a sub 3, and each of these terms has an index or a subscript, lets us know its position. And we could go all the way up to some nth term or even beyond. Okay, so each of those are terms. And when we talk about sequences, order is really important. We can write rules for sequences. So if we had a general term, a sub n equals the square root of n, we might be able to write this as a sub n equals the square root of 1, the square root of 2, the square root of 3. Keep that list going all the way up to some nth term. And it could continue going on infinitely. So another way that we might be able to write this, just a different type of notation, we could say we're dealing with the square root of n from n equals 1 to infinity. So that's just an alternate notation for sequences. And as we get into our discussion about sequences, we talk about convergence or divergence. And we've talked about converging and diverging a little bit in our class before. Converging means it tends to a specific point, and divergent means it spreads out into different directions. It doesn't go to a finite value. So sometimes numbers in a sequence can approach a single value. So we can have sequences that approach a single value. An example of what that might look like, 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, all the way up to some nth term, 1 divided by n. And so in this sequence, what we can notice is that as n becomes infinitely large, what value do the terms appear to approach? The terms approach 0. And so as they start to approach a specific number, this is indicatory, or it's an indication of convergence. We could say converges to a specific value. So on the other hand, we could have an example here. And maybe my terms look like square root of 1, square root of 2, square root of 3, all the way on to some nth square root. And in this case, as n becomes infinitely large, the terms also become infinitely large. Okay? They become larger. Maybe not infinitely large, but the terms become larger. And so adding up a set of numbers that are just getting bigger and bigger and bigger, that would be an example of something that might diverge. And another situation where we might have divergence, we can have alternating sequence. So you notice that my terms are flip-flopping, and this might be modeled by a general term, -1 raised to the n plus 1. And so these terms, you'll notice they alternate positive, negative, positive, negative. So they alternate back and forth. These never converge to a single value. And that's not to say an alternating sequence can't converge, but in this situation, it's never going to go to a specific value. It's always 1 or -1. So this is another example of a divergent series. And so we have this definition here which captures the meaning of having a sequence which converges to a specific limiting value, like a limit. And what it says is that if we go far enough out in a sequence by taking the index n to be larger, the index we're calling little n, to be larger than some value, any arbitrary value, capital N, then the difference between that term, a sub n, and the limit of the sequence becomes less than any pre-selected positive number epsilon. So epsilon being some number we've determined which is positive, greater than 0. So reading through this definition, we say that the sequence of terms a sub n converges to a number L, like a limit, for every positive epsilon. And so if you go back and you think about our definition, the precise definition of a limit, we use L for our limit and epsilon, that kind of margin of error off of L. So this converges to the number L for every positive number epsilon that corresponds to some pre-selected integer capital N, such that the absolute value of that large term, a sub n, minus the limit, is always going to be less than some epsilon value. Whenever your n is greater than that pre-selected capital N. And if no such number L for the limit exists, we then say that the sequence diverges. And what we want to remember is that if a sub n converges to L, we can write this as the limit as n goes to infinity of a sub n equals L. Or more simply, we can say a sub n approaches that value, L. And we call L the limit of a sequence. So we're seeing some pieces here that are very similar to our precise definition of a limit. And so I've grabbed this picture, which corresponds with our definition. And what it's saying, as we go out and we surpass this capital N value, so as my n's become infinitely large, what we start to notice about our outputs is that they all become near a specific L, a limit, right? And they're within epsilon, some pre-selected value of that L. So, and again, looking at the piece up here, we end up at a certain point where all of the numbers are close to this L. They're either epsilon above or epsilon below. So we have an example here, and we're going to show that the limit as n approaches infinity of some sequence 1 over n is going to equal 0. And in order for us to do this, we know we have to have some positive epsilon. So we'll say let epsilon greater than 0 be given. And what we must show in order for this to be true, we have to show that there exists, we can write that as a backwards E, there exists, but there exists some integer, capital N. So say there exists an integer, right? capital N, such that the absolute value of that term minus the limit 0 is less than epsilon. When my term, my index for my term, has exceeded this pre-selected n value. So what we can show then, or what we know, is that the inequality holds as long as, or if, 1 over n is less than epsilon, or n is greater than 1 over epsilon. And so that second part here that I've written, I just rearranged it algebraically. So if n, capital N, is any integer z, which is greater than 1 over epsilon, then this holds, or is true, for all indices which are bigger than that specified value of n. So what we can say here is, therefore, the limit as n goes to infinity of 1 over n is true, because we satisfied the definition. So we have another example here. We're going to show that this alternating sequence, 1, negative 1, 1, negative 1, 1, negative 1, going on infinitely up to the point where we have negative 1 raised to the n plus 1 power. So we want to show that this sequence diverges. And sometimes when we're dealing with divergence, it's easier to try to show that it converges and show that it doesn't converge. So it's easier to try and show convergence and fail. So we'll start this problem off and we'll say, let the sequence converge to L. So if we do that, then the numbers in the sequence eventually they become arbitrarily close to that L, right? So we're assuming it's going to converge, or we're trying to show that it converges. So if we say it converges to L, then all of the terms, all of those numbers in the sequence, they get arbitrarily close to L. However, if this keeps oscillating forever, this can't occur. So what we're going to do is we're going to choose epsilon to equal 1/2. And if we choose it that way, then all of the terms, all of the a sub n's with an index, little n, larger than some arbitrary value, capital N, must lie within epsilon equals 1/2 of L. Okay, so all terms a sub n with an index, little n, larger than some arbitrary value, capital N, must lie within this 1/2 unit of L, because that's how I chose my epsilon. And since the number 1 repeatedly occurs, this positive 1 repeatedly occurs as every other term, we must have that number 1 lies within 1/2 of L. so this value 1 must be within 1/2 of L. So we're going to show that, or try to show that, using the definition we previously stated. So it follows then that the absolute value of L, take away 1, needs to be 1/2, less than 1/2. Solving that absolute value inequality, we have that negative 1/2 is less than L minus 1, which is less than 1/2. Add 1 to both sides. We've got positive 1/2 is less than L. Add 1 to 1/2, you get 3/2. So in this situation, L is lying between 1/2 and 3/2. And likewise, we would need to do the same thing for that negative 1 term. So the absolute value of L minus negative 1 also has to be within that 1/2 distance from the value. And so working through this piece, same exact or very similar operation to solve that absolute value inequality. So I'll subtract negative 1/2, and that is negative 3/2 less than L, less than, if I subtract 1, I get negative 1/2. So this part says, well, L must be somewhere between negative 3/2 and negative 1/2. And these are two separate intervals that do not intersect. So L cannot be in two separate intervals that don't intersect. So therefore, no limit L exists and the sequence diverges. And so wrote out what I just said here.